This is August 2018, and we have our latest version code loaded into our newly built nano-based Arduino DDS-VFO for the HW-101 transceiver. It's version 0.7.0 currently. Still very preliminary, but we want to get this video made so we can demonstrate some of the basic functions here. For initial setup, once the code is loaded, we need to set the initial calibration. So we want to have the HW-101 on. We'll set it to 14.0, which is 20 meters. And we want to go ahead and press this memory button, which is button number 1 on the VFO. We want to select 20 meters. We can rotate through the choices and get 20 meters, hit the execute button, which is button number 2. Okay, now we're on 20 meters with an arbitrary frequency set up here. And we want to get down to 14.000 for calibration. First thing we'll do here is hit number 3, which is a step function, the frequency step choices, and we want to, every time we hit that button, we cycle through the various choices from high to low. There's 100K and 10K and on through down to 1K, 100 hertz, 10 hertz, 1 hertz, back to 100 again. We'll stop on 10K and then we'll rotate the encoder knob down to 14.0. Also, we have the HW-101 on. Let me turn the volume up just a little bit. We can hear some activity here, maybe on 20 meters. Let's change the step. We'll drop down a couple of steps to maybe 100. We're trying to get closer to 14.0. Let's go down to 10 hertz and we'll get exactly to 14.000. Okay, and then once we get there, we want to press the memory 1 button again, and 20 meters should still be displayed. And we want to save this, so we're going to hit the number 3 button, which is save. The choice would be save it again, number 3, or button number 2 would bail us out of here. We do want to save it, so we'll hit number 3 again. And now we have 20 meters saved at 14.000. I can hit the execute button, and it takes us to that frequency. We can just tune from there, and we're all set up. Now, the other frequency bands are now, the calibration is now complete, the initial calibration. We can fine-tune that in the next video. But if we pick one of the other choices, here's 15 meters, and we hit the execute button, and 21.09, they're not. 20 meters, etc. So the basic calibration is done. Now we need to set the offset, the frequency offset for each one of the bands by calibrating against some known source, some accurate source, to get as close to complete accuracy as we can on the unit. Now if we use the internal calibrator on the HW-101, which we will demonstrate here, that is one approach. Another better approach would be to use some external signal source like WWV, or possibly an accurate signal generator that you might have in the shack. But for now, we're going to demonstrate this against the cal signal in the HW-101. So we're on 20 meters now. We'll go ahead and turn the cal on. Again, so far we've just done a rudimentary calibration of the bands here. So let's see. We'll listen for that 0-beat signal. And it looks like we're not too far off of 14.000. Okay, so here's how we do the calibration on this. We want to set the frequency on our display to exactly 14.000. Then we want to listen to the tone coming from the calibration source. We want to hit the RIT button 1 time, which is number 2, and then we want to turn the encoder whichever way it takes to get to a 0-beat against that sound. So it's right about here, right around plus, or about 600 hertz off of actual 0-beat calibrating against this crystal oscillator inside the HW-101. So what we do next is, since we know we're 600 off, we need to go, we're 600 high, we need to go minus 600 to compensate for that. So all we have to do from this point is actually turn the volume down, go to minus 600 on our display, and hold the button number 2, which is the RIT execute button, for 2 seconds. Release it. Now hit button number 1 back to the band where we want to store this information, and that is still 20 meters. Now hit button number 3, which gives us a choice to either save it or bail out and not save it. We want to save it. We're going to hit 3 again. Now we hit the execute button to pick 20 meters, and we'll see that our zero beat now, by listening, is right at very close to that 14.0, and we're showing a minus 600 on the display, which means that's the saved offset for 20 meters. So now we need to do the same thing to the other bands. Let's pick another example and we'll run through that quickly here. Let's go to 40 meters. There's 40 meters. And what we need to do is make sure the calibration signal is on. First we'll set our desired display here to 7.000.000. Now we want to hit the RIT button one time, button number 2. Now we want to make sure we can find that zero beat signal. I think it's, yep, there we are here. So we're about 2,500 off on this particular transceiver. What this is doing is it's adjusting the frequency against, or making frequency changes that will zero this out per band. The differences are basically caused by the heterodyne oscillator crystals and their circuits being different unit to unit. So in this case, get to a zero beat right around here. We're about minus 21. We'll call it minus 2130. Okay, so we know that zero beats us down there. Turn the volume down. Let's go up to plus 2130. We have to go to the opposite side here. So we want to go to plus 2130. Okay, we want to hit button number 2, the RIT execute button, and hold it for 2 seconds. Now we want to hit button number 1, make sure we're still on 40 meters, then button number 3, which says save it, button number 3 again, yes. And now we can pick button number 2 to go back to 20 meters again. If I turn up the volume, calibration signal is still on. Let's listen. Yep, we're zeroing out right around 7.000, which is what we want. And the offset is set to about 2130. Difference here on 40 meters. In the same way, you can change the startup frequency on any band, or the memory at any point in time that you want to on any band that you're in. Simply, let's find somebody here. We're at 40 meters. Simply by hitting the memory button, we're on 40, and then at whatever frequency you're at, then hit save, save again, yes. Now the number 2 RIT button to take you back there again, and now we have that frequency saved. So anytime that we, anywhere in the band or anywhere we're at here, we want to return to that spot, you just hit 40 meters and just hit the execute button, and it takes you back to that spot. Okay. Also, the memory 1, the extra memory button, can be used in the same way. You can save anything there at any point in time. For instance, we're on 40 here now, and if we wanted to save this frequency into memory 1, you hit button number 1, rotate 2M1, hit save yes, save again, and now number 2 to get back there again. That's now saved. So at any point, wherever we're somewhere else on the band, we can just return to that point by hitting memory 1 and execute, like so. You may find a time where you need to add or subtract a specific number of hertz from your existing offset. Maybe you're calling CQ on CW on 40 meters, and you check the reverse beacon network on the web, and the majority of folks that come back and heard your CQ are reporting your frequency at, let's say, 200 hertz off from what you thought you should be, what is shown on your display on the VFO. That's easy to fix. You can make those corrections freestyle, I call it, kind of on the fly. All you do is hit the RIT button one time. Say we needed to add 200 hertz, we just go up to plus 200 to the offset, hold that RIT button in for 2 seconds now and release it. Then go to the memory button, hit that one time, verify that we're still on 40 meters, which we are. Now hit the save button once, and then the option to save is going to be hit that button number 3 again. Now go back to the execute button, the red execute, and now we've added that 200 hertz to our existing offset. And we can do that in either direction, plus or minus, and that can be done on any of the bands. Okay, let's take a look at the RIT function, receive incremental tuning. The RIT actually works in conjunction with an output signal from your keyer for CW, and that is required for the RIT to work because the keying signal tells the VFO to always return to that fixed RIT frequency to transmit. However, on receive, it's instantaneously back to wherever you happen to be listening. So here's how it works. We find a signal. It may be a DX station calling CQDX, and he's saying that he's listening up, maybe 1 or 2 kcs usually. Well, you start at the point of his CQ. In this case, we're on 40 meters as an example. Roll on up a couple of kilohertz from 32.0 to maybe 34.0. We'll listen around up here and make sure we got a semi-clear spot. Usually with a DX pileup, there'll be lots of guys calling up here. We hit the RIT button one time, which brings up our 0 offset for RIT. And from this point, the transmitter will always return to this exact frequency every time you hit the key on every dit and da. But we can slide up or down anywhere we want to listen. In this case, we want to go down right around that 2000 hertz that we moved up, and we could go ahead and call away at this point, and we'd be transmitting 2 kcs or 2 kilohertz higher. So that's how RIT works, and anytime we want to drop out of RIT, we just hit that RIT button one more time, and we drop out, and as soon as we turn the encoder knob, we're back to displaying the normal offset for that frequency band. Okay, that's how the RIT works.